each charged surface of a conducting plate behaves as a non-conducting charged sheet. Finish. So this is the thing which again our entire chapter, just the basics of capacitor revolves around this idea what we have concluded in the Gauss layer. So let's come for the condition like this. So this is the plate. This is uncharged here. So this is iron plate. Everywhere I'm considering the conducting plates only. The uncharged. So I'll give a charge to it. The first case. Second case. So when I give a charge to it. So what happened to the charge? We'll decide. It will get resided on this one. So now, so this is the initial. There's a neutral. Initially, we'll make that this. Let this be neutral. So it got charged, no? It got charged. So let me take a point 1. So what is the potential of this? It is in fact non-zero. Why non-zero? Because some charge is present on it. So potential at infinity will be 0. So potential of this is non-zero. If I want to add more charge to it, so I have to do any work is to add a charge to same plate. The same plate here already is having a charge q. Somewhere I'll write it here, or q by 2 if you want to take it. After adding charge, q by 2. Q charge is added to neutral iron plate. Fine. So now further, this was having potential 1. So to add this charge dq, now some charge is added, some charge dq is added to plate. How much of work I should do to this? dw1 should be equal to, what is the potential of this iron plate? Let it be V1. After adding some charge, it has acquired some potential. So V1 into dq, shall I write directly? Work done by X-ray agent in moving a charge dq from infinity to that point. So if you are getting confusion, so let's go back to the basic. Work done by X-ray agent. Who can add X-ray agent? Work done by X-ray agent in moving a charge from infinity to a point P on a plate should be equal to dq into Vp minus V infinity. So this is dw1, I'll write it. So dq charge, potential V1, potential at infinity due to this plate will be 0. So this much of work is what I have to do. Now further, I'll add further more charge like this. To add a charge, what happened? I have to keep on do work, no? And as after adding this charge dq, it has acquired now potential how much? Let it be, now it has become total charge, it has become now potential at this point, let it be V2. So V2 will be greater than V1. Second time I had to add a charge. How much of this? Same amount of charge I had to add up. How much of work I should do? V2 into dq. Got this idea now? So therefore, every time I had to add a charge, what happened here? I had to do work, no? And what is that work done? It keep on increases. For nth time, if I am adding charge, then definitely what happen? I should do more work here. So here, work done means what nothing but we have to spend energy. So now what is the question here now? I want to store a charge. Can I use a conducting plate? The answer is yes. We can use conducting plate. But what is the disadvantage here? we have to do more and more work when you are adding same charge nth time. Suppose say first time I'm spending 1 joule for 1 coulomb. For same 1 coulomb, what happen if I cannot I have to spend more. So first year W1 you say 1 joule. W2 what happen dW2 will be more than that. But the same charge I'll be adding. So every time when I add charge dq what happen I have to do more and more and more and work. So this will be very problematic, no? So why do this? Because we can't suddenly add a charge. It's better what happen. Can you suddenly recharge your mobile? Gradually you're going to put it, no? So first 1 minute you have to spend, say like you're going to spend 10 joules. So the next minute what happen? You have to spend 50 joules. The next, but the amount of energy you're adding is same, but you have to do work is more. So next for third minute what happen? You have to spend somewhere around say 120 joule. So like that, as you keep on add energy, add charge to the circuit, the more and more work you have to do. I think this will be totally problematic, no? Like this, to add a small amount of charge, we have to do large amount of work here. So this is the problem. So the amount of charge I'm adding is same, but what happen? The amount of work what I do is will keep on increases for the same amount of charge what I'll be adding. So with this, what I can say now as V2 greater than V1, dW2 greater than D1, but same charge I'll be adding every time. Got the idea, no? So here what we did, W1 work we did, dW1 you call. Here what happened, dW2 work we did. So how to overcome this? So what happened? One proposal it is brought here, as this is a charged conductor. This is a charged conductor. It is having a charge Q by 2, Q by 2. From far away, from infinity, what will happen? I'll bring a neutral plate. So there's the first diagram. In the second diagram, next proposal it is brought here. If I bring neutral plate, there's a neutral plate. Kept near. There's a second situation. Neutral plate kept near the plate. Okay, this is X. Neutral plate Y kept near the charged plate X. What it will do, as it was having a charge plus Q by 2, no? Because what all charge given will divide. So it will induce a charge. What it does, I think I'll take this comment here because it will acquire charge, no? Neutral plate Y, in the second situation, neutral plate Y kept near the charge plate X. What will happen to, what will happen to this plate? It will induce a charge. As it was neutral, so it will induce charge minus Q by 2 to plus Q by 2. Anything happened to potential? Earlier, what was the potential? It was V1. Now also open the potential will be same. Didn't change anything. Now second situation, the plate Y will be earthed. I'm going to earth it. You can earth any surface to make. So if I earth it, tell me what will happen. Already we have discussed some earthing concept. So due to this earthing, so first what all charge on the plate Y, let it send it to 0. Then this plus Q by 2 will be pulled to inner side. So the charge what happen will get aligned like this. This will induce a charge, will get minus Q. Look at the charges now. So earlier what was the potential? V1. Potential now V1. Now what happened to potential? Potential here will be V2. Is it V2 very much less than V1? As it is. Now, when I brought that neutral plate Y nearby X, what it does, it induce charge minus and plus. So now as this thickness very thin, so the negative charge, presence of negative minus q by 2 plus q by 2. Presence of this minus q by 2 plus q by 2 very near to this will not alter its potential. Almost its potential remains same. But when I earthed it, I got negative. So you see that what was earlier potential was due to this charge q. Now look at this V2. Due to this positive charge q will be there, and also nearby this, say at a distance some d, I kept it here. So what do you expect V2 now? V2 will be very much less than V1. Any reason for that? The negative charge what happened? The V1 was due to the charge present on this plate. The potential of this plate is due to charge present q by 2, q by 2. Now when I bring neutral plate, what happened the potential? It almost remains same. Very slight change will come. Almost we can say potential remains same here. But when I earth the plate Y, then what happened? The charge distribution will be like this. Now you look at this negative charges. It's like a definitely will reduce the potential of plate 2, no? So it has very much reduced here. Suppose say this 1000 volt, it might have become 20 volt now. Now look at this. If I want to increase this potential, can I add more charge to the plate 2? I can add more charge to bring the potential of plate X to the original value V1. So what I should do now? Because we know potential is directly proportional to charge. So indirectly now what I'm doing is to increase the potential of plate 2 to original value V1. So I can add more charge now. So what I made here? So indirectly what I did is like I just increased the capacitance of the plate X. Capacitance I'm using, capacity to store more charges. If you look at the plate X, there is some upper limit to store charges. Now you can ask questions, sir, why you brought that upper limit here? What is the maximum charge I can store here? So can you go back to radiation pressure? There's some upper limit, no? If the radiation pressure becomes greater than the tensile stress inside the material will get ruptured. So there's some upper limit for a charge to be stored on a conductor. So this is the maximum charge which I can store in the conductor one, but still I want to store more charge. So I'm bringing this setup. If I bring a earthed conducting plate nearby A, both are conducting. If I bring a earthed conducting plate nearby a charged conductor, then what will happen to potential of that will decrease very much. To bring back to the original value V1, I can add more charge, no? So indirectly what I did now, earlier it was able to store only this much of charge. Now open I can add more charge here. So what we did now, I increased the capacity to store more charges. Are you getting now this one? So I'll write the reason now. The potential of plate X can be increased by adding by giving additional charge to it. So earlier this was the maximum limit it was able to store. So what you did now, you just increased its maximum limit, no? So therefore, what we increase, shall I say that we have increased the capacitance of a conductor? Okay, sir, then primarily our focus was on the work done to put a charge, no? Let's come back to this. So what was the drawback in this system? Every time if I'm adding a first time when I'm adding a charge DQ, I did work DW1. Second time I need not to do same work, I have to do more than that. So like that when I'm adding nth time a charge, I have to do more work here. So come for this. Now earlier what when the potential was V1, no? To put a charge DQ, I should do work how much? dW1 V1 into DQ. Work done to put a charge I'll write it in order. We'll write it here. The first point, work done to add charge dq to plate X in figure 1 is how much it is? V1 into dq. Second one, work done to add charge dq to plate X in figure 3. And as V2 very much less than V1. Okay, fine. So now what happened to work done? I do less work. No? Did I do anything very big? Nothing, no? Some neutral conducting plate should be kept nearby the charged surface or the charged plate on which you want to add a charge. So what it does, it will decrease the amount of work to be done. Getting this one? I think you are getting some this one. So this is the conductor. Let's come for this. This is the conductor. Some any shape, let it be. I want to add a charge. I have to do work. Okay, that I can do one thing. I can keep on add a charge. I'll be doing work. Instead, shall I go for another method? There's a conductor X. I'll bring another authored one. Now what happens if I am adding a charge? I'll be doing less work. This is isolated conductor. In this one, so here what I have to do more work. What about in second case? I'll be doing less work. The reason for that, because if a grounded conductor is kept nearby another conductor on which you are adding a charge, so you have to do less work here. So here if you say W1, W2 will be very much less than W1. So you can ask questions of why you are giving priority for work done. To charge a mobile, we have to do work, no? We have to do work means who will do work there? That electric meter, electric current, it does work, the electrical power. So to charge a mobile, if you spend more and more amount, means to charge mobile once fully 100%. If you spend around say like 100 rupees, tell me, I think it will be a big headache, no? So per day 3 times charging, no, because of online classes, per day 300 rupees, per month 9,000 rupees will come bill only for mobile charging. Just imagine fridge, refrigerator, television, all ACs, bulbs, everything. So the monthly bill will come 25,000 rupees. Now instead this what happen if I bring a earthed conductor, then what happen? So it may charge around say like a 2 rupees, this one, for full charge. The reason for that, we have just decreased the potential of conductor. Then I have to do less work. That's a basic idea. So therefore, whenever we are adding a charge to a system, I'll follow this particular convention. What is, so there's a basic idea of this called like a principle of capacitor. So here I'm going to introduce word capacitance of a conductor. Now indirectly, so what I did for the plate X, shall I say I increased the capacitance to store more charges, because this was the maximum upper limit. Now it can store more than the charge what it was permitted. So what we did, we have increased the capacitance of a conductor. So nothing but the potential of plate X can be increased by giving additional charge to it. So indirectly, or we have increased the capacity of a plate X to store more charges. Capacity, I'm using word. So this is the first time you are seeing something I brought capacity. How that capacity and potential are related. So from this overall discussion, capacity to store charges, capacitance of a conductor is called as capacitance. That one. So how capacity to store charges and potential are related, indirectly proportional. So I'll write it here. Capacity to store charges is inversely proportional to its potential. Then how potential and charge are related? Directly proportional. Already from electrostatics. Okay, got this one. So here something this one. The capacity to store charges, this particular thing I'll define it as the capacitance of a conductor. So I'll bring the word capacitance. What is the capacitance? It's a measure of capacity of a conductor to show charges. So therefore, how capacitance is related now indirectly proportional to potential. So what is the symbol C? And how do we measure capacitance in terms of farad? So what is the unit for capacitance will be farad. The symbol will be F. So therefore, how capacitance and potential are related, inversely proportional, and how potential and charge directly proportional. Clear this. So if I remove this proportionality, I'll bring the C in the denominator, not in the numerator. Any reason for that? Because of this condition. Sir, why not V equal to QC? No, how V and C are related, inversely proportional. That's why the equation we brought it. So how potential of a conductor, charge on a conductor, and capacitance of a conductor are related. This is one basic equation. Go this one. So what is V? V is a potential. Q is a charge. Already potential, you know, electrostatic charge, you know that one. So how V greater than Q from electrostatics? Due to point charge, as you increase the magnitude of point charge, potential at a point will increase. So like this, I introduced the idea of the capacitance here. Okay, got this one. So we have started from somewhere like this. The priority was work done. For isolated conductor, as you keep on add a charge, the same amount of charge when you're adding nth time, you have to do more amount of work. So to save that work done, I brought some alternative method. I'll bring a neutral conducting plate near a charged plate X. Nothing will happen, no change happen. But when I earth the plate Y, then what happened? The potential of the plate X has come down by very large value. Suppose this is some 100 volt, it would have ended up with 1.1 or 2 volt like that. Now what happened? To bring it back the original to the original potential, I can add more charge. This was some upper limit, the charge Q. Now the same conductor, now it can store more charges here. So how I did? By just bringing some earthed plate nearby plate X. So what I did, I increased the capacitance of this. So how capacitance and potential are inversely proportional. Now let's come for the work done. Earlier I had to do work Q into dQ into V1, dQ into V2. Here I have to do less work in the third diagram. So if I want to store energy in a conductor, so I should prefer the diagram 1, diagram 2, or diagram 3. The diagram 3. If I want to store the charge, so the diagram 3 is what will be preferred here. This is called like a principle of capacitance. So what all we discussed is the topic will be principle of capacitor. Okay, let's concentrate now on that capacitance. Okay, let's go for this capacitance depends on what all. So I'll take the first one, a spherical conductor. Let me take iron sphere.